Hello everyone, today we are going to talk about periodic table trends. So I gotta introduce you to a few key terms first before we get into those trends. Alright, first key term, ionization energy. What is ionization energy? The energy needed to remove an electron. Okay, so this is important when we talk about ionic bonding. Right, elements are giving and taking electrons. Okay, so another key term we're going to learn is electron shielding. We're going to look at two different elements here, lithium and potassium. On the periodic table, they're in group 1. Lithium is just a couple tiles above potassium. So, potassium has more electron shells, and what does that do? Well, there's more electrons between its valence electron here and the nucleus, the very center. Right, we can compare that to lithium, which doesn't have as many electrons between its nucleus and the valence electron. This electron shielding causes potassium's valence electron to be held less tightly to the nucleus. Okay, so this one can actually leave much more easily compared to lithium. I like to think of this situation like a concert. So in a concert, the band is at the center, right? It's attracting people, and the people are the electrons. Your band is the nucleus. The closer you are to the band, the less likely you can move. There's probably a bunch of people around you, and you're probably stuck right in the front. However, if you're further out, you can more easily leave the concert, right? So this is similar to electron shielding, where the more people, or electrons, between you and the band, the nucleus, the less attracted you are to the concert. So if there's a bunch of people in between you and the band, there's hands in the air, phones up in there, you are less attracted to the band that's playing, and you're more likely to leave. Compared to if you're up front and you got a perfect view of the band, then you're probably going to stay stuck up front. This is similar to what we just talked about, electron shielding and the nucleus. So what kind of trends are we going to see? So we're going to look at trends for down a group and across a period from left to right. So ionization energy decreases as you go down a group, okay, because valence electrons are farther away. So what that means is it takes less energy to remove an electron from something that's further down. When you go across a period, it actually increases. We need more energy to remove an electron. So why is that? What's going on as we go left to right? So as we go from left to right, what we're adding more protons. And what that does is that contributes to a greater effective nuclear charge. Okay, think of it like 3 magnets versus 10. Here we're looking at lithium and neon, right? They're both in the second row, or second period. And so lithium's 10 electrons are actually pulling in, 10 protons are pulling in these electrons. And they're holding on to those electrons a little stronger than lithium. So what that does is that's going to require more energy if we want to get rid of an electron out here compared to one of lithium's electrons. Okay? The trends for atomic radius, I think, are pretty straightforward. As you go down a group, the size or atomic radius is going to increase. And why is that? With each row, we're adding another electron shell. Okay. What happens when we go across a period? So again, looking at lithium and neon, we got that greater effective nuclear charge happening again, which just means that our nucleus is stronger at pulling in these electrons. So what happens? When these protons pull in these electrons, so more protons in neon, that's going to actually make our atom just a little bit smaller compared to lithium. Okay? So as we go across a period, atomic radius will actually decrease. Okay, the last trend and last key term is electronegativity, which is the ability of an atom to attract electrons. In some ways, it's the opposite of ionization energy, which is the energy needed to remove an electron. As you go down a group, we see that electronegativity decreases due to, again, more shells, more electron shielding. Okay? As we go across a period, right, we're gaining more protons. And what do more protons do? Well, with more protons, then that's going to allow the atom to attract more electrons. Remember, protons are positively charged. Electrons, of course, are negatively charged. So more protons give it a better ability to attract electrons. All right, so in summary, we have 3 different trends, and each one goes across a period or down a group. So for ionization energy, we see that it decreases going down a group. So each of these will be kind of like the opposite. If it decreases going down a group, that means it's going to increase. What do you think? Where would it increase? Why would we need more energy? So across a period is going to be the correct answer here. Remember, as we go across a period, we're adding more protons, which means it's going to be harder to get rid of those electrons. It's going to require more energy. Okay, we said that as we go across with more protons, the atomic radius is also going to decrease because they're pulling in those electrons, right? So the radius decreases. When would we see the atomic radius increase? What do you think? The atomic radius would increase going down a group. Remember, we're adding more shells. Lastly, electronegativity, the ability to attract electrons, is going to decrease going down a group because of more shells. More electron shells means more electron shielding. That's going to make it hard for our nucleus to pull in electrons. So when would it increase? When would electronegativity increase? It would increase going across a period because we have more protons. Remember, protons are going to be what attract our electrons. More protons attract electrons. Okay, so there you have it. Make sure you know all of these periodic table trends. You're going to see at least one of these questions on your upcoming